Welcome everybody to our talk. It's my pleasure to introduce Wouter Swierstra, who's visiting with us for a couple of months. He is a professor, assistant professor at the University of Utrecht, and he is very, very well known in the Haskell community, and also he's done work in formal verification and dependent types, and I think he'll tell you a little bit about his interests. So without any further ado, welcome.
Okay, thanks, Javor. So I thought I'd have a first slide, which is about me, which is kind of selfish. But given that I'm here for a few months on sabbatical, I want to say a little bit about my history and my interests, and then I'll say something about the technical aspect. So I studied mathematics and computer science in Utrecht, and then I did a PhD on programming with dependent types with Thorsten Altenkirch at the University of Nottingham. And after that, I did various postdocs and worked in industry for a while. So at Chalmers, where they do a lot of functional programming and type theory, in Nijmegen, where they do a lot of functional programming and type theory. And I spent a while in industry working for a startup where we used OCaml to try to parallelize C++ code. And then I ended up back where I started as an assistant professor at the University of Utrecht. And I've worked with all kinds of functional languages, including Haskell and OCaml, but also Agda, Idris, and Coq. And every now so often I get to take a sabbatical, so I'll be here for the summer at Galwa. And I have a bunch of papers that I want to write, books that I want to read, but I'm happy to talk to anyone here about what you're working on if you think I can contribute in any way. Just grab me. Okay. So what's the tech talk about is it's about data. And if you look at data, it comes in all kinds of shapes and sizes. And the first kind of claim is that if you look at some of the format descriptions or the way that we actually describe or store or transmit information in binary, this can be a little bit complex. And as a running example, I took IPv4, and I kind of grabbed this table of Wikipedia, and you don't have to read it, don't worry about it. But what you can see here is that this is just the header containing a lot of the data in IPv4. And you can see here that you have a 32-bit word source address, and this line is a 32-bit word IP address describing the destination. And there's a lot of other bits of information there. So there's some checksum data, there's a version, there's some length information, and various other things. So just kind of, it's pretty easy to take a description like this and then take a whole bunch of words and then kind of break it into pieces according to this specification. But if you kind of read the description, there's actually a lot more going on, and there's a lot of semantics associated with these fields, in which you kind of have some subtle interplay. If you just read the description on the Wikipedia page, we'll say, oh, there's a version field, and it must be equal to 01004. So you have this field, the IHL field, which is the internet header length, and it specifies the number of 32-bit words that the header is long. So it needs to be at least 5 because there are 5 rows here with data, and then if it's longer, there's kind of some other optional data that might appear. The header checksum, it appears halfway through the header, even kind of before you've read in all the data, so that's maybe a little bit awkward. And if you look at the total length of the packet, there's a field here which says what's the total length, but that specifies the total length in bytes. And if you want to know the length of the data, you have to do some computation where you take the total length in bytes, you do that times 4, that can give you the kind of total number of 32-bit words, and then you subtract the IHL, and that gives you the amount of data that you can expect from the rest of the packet. So this, basically I just want to show you this, not because I'm particularly interested in IPv4, but parsing IPv4 and kind of validating that you have a correct packet according to the spec is not so easy. It's beyond context-free, right? Because there's all kinds of non-trivial computation involved to figure out like how much data will follow. You have to do some calculations and convert bytes to 32-bit words and some subtraction and so forth. So just parsing it correctly is not easy. And to go even further, it's just specifying it is not so easy. So this, if you look at the way this is usually done, you have these RFCs, request for comments, where you kind of describe kind of what is the format that you're interested in. There's some natural language, there might be some pseudocode describing how the checksum is computed. There might be some C structs or unions describing how various flags should be interpreted and this kind of thing. So as people functional programmers, you love types, you can ask the question, can we not do better, right? And that's what the talk is about. So what I want to try to do is define a data type for describing these kind of binary formats. And then from these descriptions, we can then generate the parsers and the pretty printers. And because I like dependent types, and I think they're the right tool for this job, so if you use languages like Cocker, Agda, or Idris, I'll use Agda, but it'll be very superficial. I'm hoping that if you can read Haskell, you can read these slides. If there's anything on there which you don't understand, just raise your hand, and I'd be happy to say a little bit more. But the nice thing about doing this in one of these languages is that you can then kind of prove this round-trip property once and for all, which says that if I have a piece of data and I serialize it and I deserialize it, I should get back the thing I started with. And crucially, what makes it interesting is that there's actually a lot of computation and type state being mixed. If you looked at kind of describing the length of the data, I needed to do this computation where I took the length of the header and the total length and subtract, and that'll tell me how much data to expect. So it's no longer a matter of just having static type saying this is the structure of your packet, but depending on the values that you see in various parts of the packet, you can see that you need to compute new types on the fly. So this is what dependent types are. Okay, so this is kind of to warm up a little bit to kind of understand what the general ideas of this approach is. The first thing you might be interested in is just kind of taking a whole list of input bits and then chunking it up into pieces. So what I'm going to do is I'm going to define a type describing how to break up a kind of big list of bits into the constituent fields. And I'm going to describe how to interpret this description as an actual type. So here my descriptions consist of n-bit words and pairs of descriptions. And unsurprisingly, I can define this kind of interpretation, which maps this FT type into the corresponding underlying type, which is mapping an n-bit word into a vector of n bits, and mapping kind of this O times into an actual pair of the T1 part and the T2 part. And this combination of having a data type describing some structure and then an interpretation mapping this data type into the actual corresponding type is sometimes known as a universe. If you've done any generic programming in Haskell, it's kind of familiar pattern. You describe some structure that you're interested in and then how to interpret the structure as a type. And the reason that this is a useful technique to do is because then you can define kind of a whole collection of generic functions over induction of the structure of your type. So now, kind of given one of these format descriptions, I can write a parser for that format. What does this amount to doing? Well, if I have a pair of things, I want to kind of parse T1 and parse T2 and kind of pair the results together. And I've chosen my parser type to take a list of input bits and maybe return an A in the list of bits which are left over. This is nicely applicative, and if you've done any parsing in Haskell, you can define combinators like the applicative combinators that you want for this. And if you need to kind of recognize an n-bit word, what you do is you kind of try to take the first n bits of this list. If there are no n bits there, you fail, because if the list is too short, and otherwise you just take the first n bits and then have the rest of the list later there. So that should be kind of familiar, I hope. Pretty printing is easy because basically we just go to throw away all the data that we have. If we have just a word, we can convert it to a list to get a list of bits. And if we have a pair of things, we can predicate the components and then kind of append the two lists together. And then we can do things like prove the round trip property that we're interested in, right? Where we say that if we have a value which lives in some description, and then we can pretty print that value and parse it back, and then we should just get the thing that we started with. So this is part of the way there, right? This is the kind of the first very simple thing that you might do. But there's a few kind of problems with this approach. So we have a very limited language for describing products of fixed type words, fixed size words. And in particular, we don't have any way to talk about variable length fields where we, for example, might want to read in some information about the length of the data which follows and then read in that much data. So we don't have any dependencies between the value of one field and the type of the remaining data. And we don't have any constraints on the values that the fields might assume. So we can describe a checksum field and say, okay, yeah.
So you have the round trip property. Do you prove kind of the other property that if you parse something and that parse succeeds, that you can reprint it and do the same serialization?
If you parse something and that succeeds, you could prove it the other way around as well if you want. Yeah, yeah. So this is, it's kind of, it doesn't always hold, depending on, so you have two of these properties, right? And sometimes, depending on formats,
Right.
I think.
It's not a unique serialization.
Yeah, yeah. You might not have one. I think for the things that are in this talk, I think you always have unique serialization. But that's just the characterization of the formats that we looked at. I'm not sure if we'd have to think about whether there are examples of file formats or anything which have non-unique serializations which we could still describe in this setup. But I don't know.
So, for example, PDF and many other formats have some sort of header at the front that's like a table of offsets into the file where you can find certain objects.
Yeah.
So you just shuffle them around and
Right.
the same PDF in some sense.
Yeah.
Or even a simpler example, I've seen like representation of arbitrary size numbers by having like, oh, there's going to be this many bits, and then you might have extra leading zeros on a bit that maybe when you print it out again, you won't include those.
There might be things like that, sure.
Right.
Okay, and what's another problem here is that we don't have any constraint on the values that fields might assume. So we saw that the version field in IPv4 needs to be 4, or that the checksum, we expect there to be some kind of relation between the value that the checksum assumes and the values of the rest of the fields. So to fix this, we need to go from programming with simple pairs to programming with dependent pairs, which is sometimes called sigma types. So this is how you might define a data type for pairs in something like Agda or Haskell, right? Where you have an A and a B, and then you can describe a new type consisting of a pair of an A and a B. And to build one of these pairs, you need an argument of type A and a kind of a first component of type A and a second component of type B, and then you can pair the two together. But if you look at the type of the constructor here, it's kind of non-dependent, right? It takes an A and a B and builds up a pair. But what if this was actually kind of a dependent constructor where the B here could depend on the first component? So then you get something like this, where instead of just having an A and a B, you have an A and a B, but B isn't just a type, it's a type which might depend on A. And then the type of the constructor changes in that you have an X of type A and a B of X, and then you can pair these two together somehow. So this, if you look through a kind of logical perspective and the whole Curry-Howard story, this is similar to existential quantification. So if you have a sigma natural number such that that number is bigger than 7, that will consist of a choice of number, which could be 9, and a proof that 9 is larger than 7. But this is exactly what we need to kind of describe dependencies between fields, where we can have some part of the information, say, which might specify information about the length, and then the second component can then actually refer to that, the value of that length to compute the rest of the header. This is kind of making our universe one step more interesting. So what do we do is, well, we had words and products. Now I want to add some more interesting stuff to that. So what I'll do is I'll add a new constructor for sigma types, which will allow me to describe dependencies between fields, so that the value of one field can determine the type of the remaining fields. And I might want to add fields which are calculated or derived somehow. So interestingly, what you can see now is that I actually have, where previously I could actually have a data type definition and then separately specify this is how to interpret this data type as a type. What I've done here is I've given a data type definition, and here's the interpretation of that data type as a type. But all of a sudden, they become mutually recursive. And in particular, you need that for the sigma, because, so what I have here is I have a choice. So previously, the pair said some format type and a format type, and I'll build a new format type. And here for sigma, now I say I choose a format type, and then instead of just having a format type, I actually have a function which, given the value of this field tells me how to continue. So I can map, and the interpretation just maps sigma to the sigma types that I showed you in the obvious way. These calculated fields, they have some format type and the value that I'm expecting there, and that'll give me a new format. And then I'm not interested in kind of storing any information about calculated fields, so I'm just going to map that to a unit type, which doesn't contain interesting information. So let's look at some examples. Suppose I want to describe a checksum byte. So what I could do is I could say I have a sigma type with a 7-bit word, and then after the sigma type, I have a calculated field, which is a word of length 1, and the value that it stores there is just a parity bit, where parity is some function which computes the parity of an n-bit word. So this describes a 7-bit word followed by a single parity bit of that word. So what's interesting is previously I could describe a 7-bit word followed by a 1-bit word, but I couldn't describe the dependency between the two. So now all of a sudden I can say the 7-bit word and then followed by, I can describe exactly what field I'm expecting there, namely the parity of the 7-bit word that preceding it. And then if I kind of take the semantics of this thing, it becomes a sigma type of a 7-bit word and the constant unit, some uninteresting data. So this is kind of the other kind of thing which I was interested in doing, is having a length field, right, where I could say I have a dependency, once again, so I have a sigma type, I have a 32-bit word, and then followed by that is another word, but now I want to somehow interpret the length information, the d that I have, as a natural number. So I convert, I don't know, this to a natural number. So this is the situation which you have quite a lot, where you have, here's a length field followed by that many bits. Yeah?
Does this only work with followed by?
That's a very good question. Give me 2 minutes, and then I'll get back to that. So the corresponding type is, once again, we have a sigma type where we have a 32-bit word followed by a vector of that length. Okay, if we want to parse this, once again, we can kind of update the parse function that we saw previously, and the products and the words are kind of unchanged. For the calculated fields, we can try to parse the value of t, and that'll give us a y, and then we check that x and y are equal. And if they are, then we can return just, otherwise we return nothing. For parsing sigma types, it's almost the same as parsing pairs. We can't quite use the applicative combinators because we have some more interesting dependency going on between the usual applicative combinators. Because in particular, kind of the type, I mean, we want to access y here when we call the second part of the parser, and that's not something that you can do using the regular applicative things. Okay, so then we can update the pretty printing function and the round trip proofs, and that all works. And then in an ideal world where kind of all file formats are defined by type theorists, we would now be done, right? Because this is what we wanted. We wanted to describe dependencies, and we wanted to describe calculation and derived fields or constant fields. But that's not the case. And there are kind of two problems here. And this one is the one kind of which Eric mentioned, is that if we have these computed bits of data, sometimes we or the only dependencies that we can really describe are we kind of have some data and then some data which depends on that. We can't have backwards dependencies. And this is something which shows up if you look at IPv4 once again. If we want to describe the checksum of the header, it occurs halfway through the header. So if it was like at the very end, we could just have a sigma type saying, read in all these fields, and here's the checksum of all those fields. But it's not like that. The checksum appears halfway through. So we need to kind of have a story there. And some of the computations involved are really messy in some of these realistic formats. And ideally, what we'd like to do is be able to say that, make it a little bit more kind of decouple the actual encoding of the binary information from the computations that we're doing. So if you look at, let me go back. Here, we have to kind of say, interpret this bunch of words in some certain way to kind of turn it into a natural number. And maybe we don't want to do that. We want to say kind of just read in a natural number and then a word of that length. And then later we can specify, by the way, this natural number really interpret that as a 32-bit word, which is kind of encoded using little endian, what big end is or whatever. So that's the challenge here, that there are two problems that we still haven't addressed, namely kind of backward dependency, referring to things that we haven't seen yet, and having to kind of mix encoding information together with the actual dependencies that we're describing. So this is the plan of attack, right? And we're going to define a richer universe of file formats, which kind of contains arbitrary types, and because that's nicer to work with. For a lot of these dependencies, they involve more complicated computation, so we don't always want to work just with bits, but we're going to say, oh, here's a natural number, and then the natural number must be bigger than 7, and then if it's whatever, that we can compute the remaining fields in such and such a way. And then we want to make but of course, if we have these natural numbers there, we haven't specified what the encoding is of these natural numbers. So, or there could be data there which we don't know how to serialize. So we're going to define a predicate which says this file description is trivial somehow or low level, and the kind of idea is going to be that if trivial kind of these low level descriptions are very easy to parse and predict. And then we're going to define some transformations on this original universe, which either kind of specify how to encode data, or maybe they insert new fields and kind of modify these descriptions. So that'll hopefully give us a way to start with some high-level description of what is the data that we're interested in, and then we can kind of step-by-step add information about how to encode that data as in binary, or how to insert fields or derive fields like checksums or version fields. That kind of thing. So that it's almost what we had previously, but now we want pairs and sigmas because we want sequencing and dependencies. And we just have leaves, and these leaves can now just store arbitrary types. So if we have a leaf of A, we just interpret it as A. So it's very little structure at this level, right? We just want to know what are the fields that you're interested in, kind of pair them together. If you have any dependencies, make them explicit using sigma types.
One more question.
Yeah.
Do we need the second constructor?
No. So we don't need both products and dependent products. We could encode one with the other because the sigma types are strictly more general. But it's usually useful to distinguish between the two concepts because they're kind of notionally different, saying there's a real dependency here or there's just sequencing of fields. And sometimes the products are a little bit easier to work with at times because you know there's no dependency and you just have kind of like something like binary trees as opposed to functions which you're going to have over here. If you want to traverse these things or, I don't know, pretty print the actual description, right? If you know that you just have products, you could say, oh, here's all the products. And if you have sigma types, you actually have functions here, which are harder to print. So that would be one example where having the distinctions. So another kind of point of criticism that you might have is that we're kind of describing a data type which contains arbitrary sets, arbitrary types. So if you know any type theory, you know that actually if you say the kind of star or the type of set, it's not set again, it has to be something bigger, so it has to be set 1. Because otherwise you can, it's like Russell's paradox, where you have the set of all sets. If that's once again a set, you can derive a contradiction. If you can have a type of all types, your type theory becomes unset. But this is a slightly technical point, and it's easy to solve if you pay a small price, in that you could say, well, actually, I could make a separate, instead of having kind of quantifying over all sets here, I could have a separate kind of base universe describing the data that I'm interested in, and then layer this on top of that. But it's, I'm going to ignore all of these kind of size issues for the rest of the talk. So now what I can do is I could actually say, if I want kind of a length field followed by a word, I could say, well, I want a sigma type, which stores a natural number, and then the second component of the sigma is just a vector of bits of that length. And then here we haven't said how to encode this natural number. It's really just saying there's a nat and then a vector of bits. Now the problem is, though, that our descriptions can contain arbitrary data. And so in particular, they could contain anything of type A, so that could be functions, it could be all kinds of stuff in there. So we don't know how to parse that. But the good news is that if we kind of make the assumption that all the data, all the types, all the A's stored in the leaves are just binary words, it's very easy to parse, because that's what we did when we started off. So if we can kind of define a little predicate which says, essentially, everything in the leaf is a binary word, so that's saying that when is one of these descriptions low level is when all the leaves are binary words, if kind of both components of pairs are binary words, and sigma types kind of correspondingly, everything is just a binary word. It's very easy to parse. So if we can kind of just modify the parse function that we saw previously, essentially, saying that under the assumption that everything is low level, we can still derive a parser. And these proofs of this low level predicate, they're so structural that they can be pretty much generated automatically. Given any description, if it's a pair, you try to kind of prove it for both components of the pair. If it's a leaf, you just check whether the type there is actually a vector, is vector fits. And for sigmas, likewise, kind of Agda has some very, very simple proof search mechanism, and that's good enough for most of the cases.
So when can't you do it automatically?
When can't you do it? If you have some kind of computation in the sigma type where you inspect this data and then you branch. And then you would need to have a little lemma which says that if both branches are okay, it'll work out. But yeah, that kind of thing. But for kind of most simple stuff, it really is quite simple. So the good news is now, this is kind of getting there slowly, that assuming all of our data is just binary words, we're done. We can call our parser and we can kind of adapt our pretty printer and kind of, we have the round trip property we want. But at the same time, we kind of gave up on having the fact that we could actually rely on all of our data in binary words, because we wanted to have natural numbers because they're easier to work with to describe the dependencies. So what we want is we want somehow to describe a conversion or an encoding, essentially. And to do that, we can define this little relation between two of our descriptions, where we want to have a kind of an encoding function and a decoding function. And we'll let the decoding function fail because we might be kind of, we're not losing information, but we might be decoding into something which is bigger. Suppose you have a flag which could take 3 valid values, and you describe it using 2 bits. There's kind of 1 bit there which you don't know how to interpret. So for that reason, the decoding might fail. And we want the property that, if we encode something and then decode it, we get a thing sort of. So this is a semi-partial isomorphism. But you can think of it really as being a shift in representation, saying here's a bit of data which I want to encode in a certain way in binary. So it's just kind of describing a translation between semantics of T1 and semantics of T2. These things are nicely closed in the composition. There's an identity conversion that you can define. It's all kind of good properties to have. So in particular, this explicit congestion notification field in IPv4, you can describe it just as an enumeration with 4 constructors. You can show how to encode it as 2 bits, and decode 2 bits into one of these things, and prove the lemma that you want. And so now, if we want to describe IPv4, we can just say that we want one of these fields, and what we then want to do is this is the ingredients we need for describing a conversion between the ECN field and the actual bits. But now, suppose we do this for all the fields of IPv4, then kind of we want to be able to apply different conversions to the different fields. And that's kind of, this is the last data type that you'll see. But now we need to massage it a little bit to get exactly what we want. So what we'll do is we could just kind of define arbitrary functions which apply conversions and kind of manipulate our description types. But instead what we'll do is we'll try to make it instead of have to work with arbitrary transformations on our descriptions, we're going to make it slightly more structured and say that we can define a data type, DTX, describing some transformation on our descriptions. And this is typically going to be a conversion, kind of a shift in representation from T1 to T2. But maybe we want to, if we have a kind of composite description with a bunch of fields, we want to treat the different fields differently. And then we can have these pairs specifying, oh, treat this field in this way and that field in that way. And the same for sigma. And once again, there's an identity thing, that transformation, and it's closed under, you can take the reflexive transitive closure of this thing. So, coming back to our example, we had this description where we wanted a sigma with a natural number and a vector of that many bits. And now we can describe the encoding and saying that we're going to use sigma once again. So I've chosen the same constructor names for the DTX and the DT. So we can mimic exactly what the same structure that we have up here. Where we now just say, we specify that we want to use the whatever int32 encoding of natural numbers here, and then copy over the other data. So we're adding more information about how to kind of actually serialize this information by describing one of these transformations. And this is, if you look at realistic descriptions, it really starts to pay off, being able to work with natural numbers rather than bits, having to serialize them, or even if you look at these lengths in IPv4, it's actually pretty complicated. So maybe you want to have some more abstract representation of what the fields should mean and describe the dependencies, and then later say, oh, actually, I have you could kind of conceptually, this is what's going on in IPv4. But it's not really the case, because it's not that you have this single length field, but this natural number is actually kind of split into two parts, one which describes the length of the header and one which describes the total length. And then you can refine your representation iteratively a bit. Yeah?
So I've lost a small detail, which
okay.
is, so what exactly happens when we pick a length that's bigger than an int32 can represent?
Yeah, I'm cheating here. That's well spotted. There is no conversion between nat and int32. So what I should have chosen here is either a nat, and a proof that nat is less than 2 to the power 32, or use another data type like fin, which is bounded more explicitly. So I'm, for the sake of kind of fitting on a slide, sure. I'm cheating a bit here and there. Yeah. There.
What are we getting out of having both a DT and a DTX?
So this is the approach that we've taken, is that you start by just kind of describing at a high level, this is the information that I'm interested in. And then kind of this DTX is then describing the transformations that you need to get that information into binary, essentially. Could you do it in one step?
Is there multiple ways to DTX and DTY? There's different predicates on these DTs that are useful to have?
No, we have just one DTX, which is describing the, in this, so far we've just seen conversion, right? Changing data representation. I want to next thing that we want to do is insert more fields like checksums or things where we have dependencies going on. And then having, kind of separating, so if you want to describe a format, you typically start by saying, here's the high-level data that I'm interested in. I can start with something like, this is the ECN, right? And this is how I want to convert it. And then you start by just saying, I want this ECN field, and maybe this information, this information. I can describe it, and together with any of the dependencies and calculations going on, just as one of these DTs. And then later on, I can layer on more information, saying, oh, by the way, this field is encoded in binary in this way, or actually I have this natural number here, but that's actually an aggregate of other kind of smaller fields or anything like that. So if I have one of these transformations on T, I can compute the resulting data description. And if I have a value of type T, I can kind of run all the coercions in there and get the corresponding value, the transformed value, so to speak. Okay, so these were the two problems that we started off with. That we had computations; they were mixing encoding information with the actual dependency calculations. And what we've done by kind of splitting this out and saying that we can kind of start with descriptions containing arbitrary types independent of the encoding, And then we can layer on these transformations saying, please convert this type into binary in this style. We can kind of decouple that. So that's done. And then we had the problem with having computed data where, so in the simple example where we had sigmas, we could see how to refer to previous values, but some of these checksums, they also refer to future values. So if you the checksum for for IPv4 comes halfway through the header. So that's the other thing that's kind of still missing. So the nice thing about having this DTX now is that we can say, okay, we want to kind of handle a new kind of transformation, namely inserting new fields. So I'll add a new constructor to a DTX type saying, we're also allowed to insert new fields. And crucially, we'll add a new kind of extra argument to DTX saying, this is the entire description that you're transforming. So that way, if you want to insert a field kind of like a checksum halfway through your data, you kind of describe this as a DTX over all of your data, and then you have that at your disposal when you do the insertion and kind of calculate the checksum. So what's the type of this insertion here? So we have a T prime, which is kind of, this is the type of the new data that I want to insert. I can choose whether it should come before or after. So that's a side to the left or to the right. And then I have this function here, which will take all of my top level data and then compute a T prime from it. So this is the type that I'm inserting, this is where to insert it, and this is describing how to take all of my top level data and compute a value of the thing that I'm inserting. So here's an example. If we start with this kind of, we had a length and a word, and we had a binary serialization, and then we want to add a checksum field to that. What we do is we describe that we want to do an insertion on T, and then we have, what do we want to insert? We want to just insert a single bit. We want to insert it to the left of T, so it'll come before T as opposed to after T. And then how do we compute this data? Well, we use some checksum function, which will take the entire meaning of T and then compute a bit from that. So this gives us a way to insert a checksum before the data has actually been parsed. And then we need to just kind of update all of the functions that we had using kind of describing how to calculate a new type. And this is kind of interesting, I guess, so I have some of the code here. That if you have an insertion of a T prime to the left, then you take your original type T and you kind of pair it with a T prime before. Or if it's an insertion to the right, you do it to the right. And then you need to update the extent value functions. I don't want to go into that right now. There's one question that you would be right to ask is, how can you compute the checksum if you haven't seen all of the data yet? Crucially, we can only parse stuff once it's level, which means that we know the size of the checksum, and we can at least chunk up the size of the checksum and read that in. But we need to define an additional function to check after we've read in all the data whether the checksum really matches up with what we expect. Or kind of alternatively, we can update our parse function to include a call to check, so that once everything is parsed, we check and make sure that there's no mismatch there. So it's not like we can kind of suddenly look into the future and see what kind of data we're receiving, we're going to receive. But rather, we still need to do this, but we can also integrate it into the parse function. There's one kind of technical point that we ran into, is that if you looked at the kind of insertion function, we take the meaning of our top-level type and compute something of T prime. And if you look at some realistic formats, some of the problems we ran into is that sometimes you actually have kind of conditional extensions or conditional insertions. I've tried to come up with an example which fits on one slide, which isn't like too complicated. So I hope this kind of convinces you that this is a problem with this. Suppose we have a description which says we have a sigma with a number and that many bits. And then we want to extend this description with, we want to kind of cache the maximum, this should have been a vector of numbers, of course. Okay, whatever. We want to cache the maximum bit in this vector. So what we do is we have an extension where we copy over the length field, and then we try to insert the max. And this is the insertion of the max here. So we get our length field, and we need to kind of calculate some new transformation on the bits that we have. And if the length is 0, we just copy over the empty vector. We want to insert, I don't know, say we want to insert the sum of all the bits or something instead of the max. And we want to kind of insert it after the data that we see. If you look at the type of maxvec now, that's the kind of insertion function, which will take the semantics of the top level data and compute the natural number. It will kind of take a sigma type, which is all the information we have available. And we only ever want to do the insertion if we've checked that the vector. So we're kind of given too much information, right? We'd like to only have to worry about one case where the vector is non-empty. So this is a slight drawback, but we can fix this, but it requires a little bit of work. So the idea is that we, instead of taking a function which takes all the data and computes a t prime, we take something which takes all the data, the value of the subtree that we're currently at, which is somehow related to D through the selection, and then compute. And then we need to update kind of our DTX a little bit, where we define the subtree relationship between various DTs, and then as we kind of go down, as we define our transformations, we kind of record the path to the root, so that whenever we want to do an insertion at one point, we only have to worry about what is the data at this point, rather than what is all the data. And that lets us we can then define a more precise type for the insertion, which lets us not have to worry about empty vectors if we've already checked whether the vector is empty or not. Okay, so what did all of this work get us? So we have this universe DT, which is closed under products and dependent products and kind of arbitrary types. And then we have a predicate which says the elements of this, when kind of a type in this universe is very easy to parse, because it just contains binary words. And then we can define generic parse and predicate function, which kind of satisfy this round trip property that we're interested in. And then we have transformations, which kind of let you explain how to convert the values which live in this universe into binary words, or how to insert new fields, which can depend on arbitrary parts of the rest of the data. And together, this is like I'm hesitant to use the word DSL because it's we're not actually defining. It's not a language. We're just defining types. So it's a DSL in the same sense that if you've looked at things like Servant, this kind of Haskell web server where you would just specify what the types are of the various routes that you could take that your web server supports, and from that it'll just generate a whole bunch of functionality. So it's more like a domain-specific language for describing various types, and then from these types deriving new functionality. So what does IPv4 look like? So this is a work together with a master's student, Marcel, and he did a lot of the work, and he's very thorough. So he came up with a complete specification of IPv4 in Agda, and using this language, and then generated the parsers and predicators from that. So there are a lot of problems with this, where we had some option fields, which may have been there or not, depending on the header length, the total length, which was in there, but kind of things that we have to worry about. So we have kind of fixed enumerations or flags where they say like, this field is one of these values, and this is really easy to do, right? You just define a data type, these are the possible values, these are the encodings, and you're done. A lot of them are bounded natural numbers where they have like, here's a 32-bit word, so we could just represent that as a fin of length 2 to the power 32. Or we can describe it as a natural number and a proof that it's less than 2 to the power 32. And then we can have actual conversions describing how to serialize these numbers back into binary words using little n or big N. There's some constant fields there, like the version field, which needed to be 4, so we can, which is easy to do. We can just insert these into a description. And you have some variable length words, and these are typically easy to describe by just having a sigma type saying, here's the length of the data, and then the actual data which follows. But the calculations involved are messy. which is, I think it's not a thing that we can solve, it's just an artifact of the protocol specification, essentially. So, to get a complete description, we started off with just, once again, describing the DT, saying this is the data that we're interested in, rather than having like a flag as a 4-bit vector or something. We just have the various alternatives that these flags can be, just as a data type, and then separately we would kind of specify the encoding. So we start off with all the information that we're interested in, then we insert certain constant fields, and we kind of massage the lengths so that it's easier. It corresponds to the actual specification where these are the lengths that are easier to work with. And then we describe the binary encoding of all the high-level data, and then finally we insert some checksums which rely on this binary, that we have the binary information available. And then we can compile it to Haskell, and we can test against existing IPv4 implementations. Then, of course, because we've proven our round-trip property correct, we know that our definition is okay, but if not, we found a bug in that we were using the wrong encoding, little endian versus big endian. But it's actually good to show that you could do all this formal verification, you still need to test your code. Yeah.
So other than that endianness switch, did you try doing something like just capture a whole bunch of traffic and see if there's anything that did not parse?
No, I don't. I'm not sure how much actual traffic we've parsed or anything like that. We've looked at. I think Marcel looked at some test data and just ran through it, but nothing. We haven't stress tested it. And if you look at, I'm not sure.
Well, it could be that some of them are generating invalid packets too.
Yeah,
That would be
yeah,
kind of
yeah.
interesting to see.
Yeah, that would certainly be interesting. It would also be unsurprising because if the actual specification, especially if you look at the options field, which is now just like maybe there or maybe not, but it's really pretty messy to see kind of what goes there or not. And having a complete specification with all the possible flags and options and things, even the ones which are never used, is still a lot of work. So there's a bunch of things which we haven't done. So our parsers return nothing, which is not very informative, so we should really do better there. And the way that we wrote this, if you look at the descriptions, we typically have a whole product of things, and then kind of in comments we say, oh, this is the ECN field, this is the IHL field, blah, blah, blah. But we don't have a way to name these things or anything like that. So either using reflection kind of records, where you could actually then name the fields, or using just attaching string tags or some type tags or whatever, just somehow some way to specify more kind of what are the semantics of this data. And then a lot of the proofs involved, and these inequalities, are not very fun to do in Agda. They're kind of messy, and that's where Cork really is a better tool, because we ended up having to do a lot of these things where the length calculations, where you have to show that this number is still within the right bounds, and it's obviously the case, but you still have to convince the Agda of this fact. So what are the kind of the take-home messages? So I think a lot of people will have seen generic programming before, where that's where you use the type structure to derive new functionality for you. And in this domain, what we've done is not just kind of take one description, but we've actually had to transform a description somehow to accommodate for certain external constraints, because a lot of the times these just kind of the existing binary formats and protocols, they have a certain specification. We have, even though at a high level we can describe kind of the interesting behavior,